Okay, so last time we proved that if f from n to e is onto, then e is at most countable, right? If you have an onto function from natural numbers to the set e, then e is at most countable. At most, it can be finite, it can be countable. Okay, so that's what we proved last time. Now let's continue the discussion. 1.37. Suppose that A and B are sets. Then the first statement, if A is a subset of B and B is at most countable. B is at most countable. Then A is at most countable. Okay, so the superset is at most countable, then the subset is at most countable. And the other way, if A is a subset of B and A is uncountable, then B is uncountable. Okay, and part 3, the set of real numbers is uncountable. Okay, this is a very simple conclusion from the previous theorem, from this result. We just go through it quickly. It's not tricky. Okay, so B is at the most countable. Then there is a function g from n to b. There is an onto function g from n to b, right? Then if A is empty, then A is at the most countable. There's nothing to discuss, so it's a trivial case. If A is not empty, then choose an element A0 in the set A and define we define another function f from n to a by fn. It is equal to g of n. It is equal to g of n if g of n is inside A. It is equal to g of A is sub 0 if g of n is not in A. It's not in A, okay? So when it is outside of the image, outside the subset, you just pull it back and randomly, I'm sorry, not g of A0, just A0. Just name it by A0. All right, then this is the F is onto. and A is at most countable. A is at most countable. Whenever you get onto function, then you will get a at most countable set. Okay. So that's it. And second, so we know in the classification of the cardinality of the set, like the number of the elements in the set, we have only two parts. I mean, in the definition we have three parts, but if we consider at most countable, we have two parts. One part is uncountable. The other part is at most countable. It is uncountable, then it is not at most countable. It is at most countable, then it is not uncountable. They are disjoint part. They cover the whole possible sets, all possible sets, okay? So here, in the second part, we want to show that B is uncountable. We prove it by contradiction. Assume that B is at most countable, opposite. If B is at most countable, A is a subset of B, then by part A, by part 1, A is at most countable. But the assumption says A is uncountable. Contradiction, right? It's a contradiction. So it's never, so the B cannot be at most countable. B is uncountable. So from part 1 and part 2, we have a common sense. I mean, based on those two parts, we have a common sense. The common sense says if we want to show A at most countable, we can find, I mean, it's one possible way, we can find A in B and B at most countable. Right? Sometimes maybe you extend your range, you have a bigger set. The bigger set is easy to prove. Well, who knows? And the other one, if we want to show B uncountable, we can find A inside B, a subset of B, and A is uncountable. Right? So you can find a small set, and small set may maybe already have the property that it is uncountable. Follow this idea, we prove the part 3. Okay, so we already know that from the counter's diagonalization argument, we know that the interval 0, 1 is uncountable. And of course, interval 0, 1 is a subset of real numbers. Hence, by part 2, R is uncountable. right? A small subset is uncountable, then the superset is also uncountable. All right. So that's the statement about the set, a superset and subset. And next, let's talk about the Cartesian product of two countable sets and the countable union of countable sets. Okay, theorem 1.3838. So let A1, A2, dot, dot, dot be at most countable sets. Okay, so you have a sequence of countable set. Actually, you have a countable sequence of at most countable set. Part 1, then A1 cross A2, the Cartesian product of two at most countable set is at most countable. Part 2, if E is the union of all Aj, J belong to the natural numbers, or you can write this way, the union of Aj, J is from 1 to infinity, the countable union, then E is at most countable. E is at most countable. So we're going to show this theorem. Right? Okay. So proof. So A1 is at most countable. Then there exists an onto function phi1 from n to A1. And you repeat this for An is at most countable. There exists an onto function phi n from n to An. And you continue this process infinitely many times, countably many times. Hence, we can define an onto function f from n cross n to well, no, this is the first one. Yeah, my bad. We only need 1 and 2. Phi 2. This is n. This is 2. No, I'm thinking about the second part. Okay, so my bad. Just 2. Phi 1 corresponds to A1. Phi 2 corresponds to A2. Then we can have an onto function f from n cross n to A1 cross A2. Yeah, my bad. This one. There's no dot. All right, and we define it by f n m is equal to phi 1n phi 2m. Phi 1 and phi 2m. So this is a Cartesian product. Because phi 1, phi 2 are both onto functions, so this f is an onto function from n cross n to a1 cross a2. And if we can define another onto function, this is a natural idea. So up to this moment, it's a natural conclusion, natural condition. But if we can define another onto function, g from n to n cross n, if we can do this, then f compose g will be from n to n cross n. Remember, they are onto function together, both. From n to n cross n and to a1 cross a2 is onto. The composite function of two onto functions is still onto function. All right? So the problem is, what is the construction of this G? What's this construction? Okay, so the idea is the following. One, this is the first point. Okay, we are talking about natural number. Natural number starts from 1, 1, 1. And then you have 2, 1. And 1, 2. You have a, yeah, let's go this way. 3, 1. 2, 2. 1, 1, 3. So we go this way, and this way, and 4, 1, 1, 2, 3, 4, 4, 1, 3, 2, 2, 3, 1, 4. Okay, so every time you start from 1, 1, so your G will map 1 to 1, 1, the point 1, 1, and G2 will be 2, 1. G3 will be 1, 2, and G4 will be 3, 1. G5 will be 2, 2. So this is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's like the zigzag. Basic zigzag is this way. So you go up and go here and then go down, and this way. But let's always start from the bottom to top. It doesn't matter. And G6 is 1, 3. Okay, so this is the visualization. How do we define this G from the natural numbers to the to all the lattice points in the first quadrant? All right, so let's see how do we literally define this. How do we literally define this? So the first, you see here, you have several slant lines. This is the first slant line, the second slant line, third slant line, fourth slant line. Okay? For each slant line, the first slant line, the sum is the sum of the what? Of the xy coordinates is 1 plus 1 is 2. In the second slant line, the sum of xy is always you see 2 plus 1, 1 plus 2, It's always 3. You can actually prove it by mathematical induction. The nth slant line, the sum of the xy is n plus 1. So the nth slant line, the sum of xy is n plus 1. Okay? Okay, so let's see. The thing is that assume the image g of j lies on the nth slant line. Nth slant line. Nth slant line, then g of j is going to be what? The L n plus 1 minus L. L n plus 1 minus L. You see here, this is a n plus 1. The first one, L is equal to 1. L is from 1, 2, 3 up to what? Up to n. We always that's the way we say we always start from bottom to top, from bottom to top. Okay, so L is a 1. This, for example, n is a 2. So L is a 1. This is a 2 1. L is a 2. This is a 1 2. Sorry. This is let me see. L is a 1. No, the other way. N plus L, n plus 1 minus L and L. Yeah, this way. This is better. I want this way. It fits out my setting this way. So for n is equal to 2, L is a 1. This is 2 1. Yeah, this one 2 1. L is 2. It's a 1 2. Right, correct. Now it's correct. This way. In the book, it's the opposite order. It doesn't matter. Okay. Okay. So g of j is equal to this corresponding point. The problem is, what is the value of n related to j related to j? When we say we assume g of j lies on the nth slant line, then what is this n? How do you know the value of n related to j? Okay, so j is on the nth slant line, so it should be strictly greater than. You see, first slant line has 1 element, second slant line has 2 elements, third slant line has 3 elements. So nth, this j should be strictly greater than 1 plus 2 plus 3 plus up to n minus 1. And this is n minus 1 over 2. This is n minus 1 over 2. Right? Okay, so it should be strictly greater than it. And this n should be the maximum value. Maximum possible, because j is on the fourth line. Of course, it's greater than the sum of first 2. It is also greater than sum of the first 3 slant lines. But you need the largest possible one. For the integers, natural number, not integer, my bad. For the natural numbers, there's no greatest number. It has smallest number. Okay, so let's see how do we go through it. J, of course, is greater than or equal to 1. Then j plus 1 is greater than or equal to 2. And j plus 1 over 2 is greater than or equal to 1. Then j times j plus 1 over 2 will be greater than or equal to j. Right? So go this way, and eventually we have this. So this implies if we get the set E such that J is less than or equal to K plus 1 over 2, then this set E is not empty because at least the J is inside. So J is inside. In the textbook, the author said use Archimedean principle. I don't see why Archimedean principle can be applied here. Remember, Archimedean principle means for any pair of two positive numbers, A and B, there is a n so that B is less than n times A. But AB should be independent of n. This here you have K and K. They are both functions of K. I don't see how you get it. How you get some relation like this. Anyway, this works. So we get E, a subset of natural numbers, which is not empty. Then by the well-ordering principle, there is E has a least element. We call that a least element n. Okay, least element n. We cannot say the greatest integer, a natural number n, but we can say the least natural number n. Right? Greatest, we don't have any axiom to claim the greatest stuff exists for the natural number set. Okay, E has a least element, so J is less than or equal to n plus 1 over 2. n plus 1 over 2. This is a least element. Whenever you choose another natural number smaller than this n, it will be, this condition will not be satisfied. This will be satisfied. All right? So once you get this, you are going to write G of J as one of a condition. So how do you get this? So you will get G, L, what is L? L is equal to J minus n minus 1 over 2. n minus 1 over 2. L is this quantity. Right? So you will count from first, second, third, and so on. All right? So this is a fixed stuff. So we know what n is and what L is, what n is and what L is in the proof. All right. Okay, so this part we didn't use the Archimedean principle. Again, I don't see the reason why we can apply Archimedean principle. This part we use that well-ordering principle. Okay. Okay, so we do prove that if you have two at most countable set, then the Cartesian product is countable. The reason is that this is because of this setting, and also we get that the n cross n is countable. N cross n is countable because this function is not just onto; it's also 1-to-1. Yes, 1-to-1. It is also 1-to-1. So n cross n is countable. Later in the exam, maybe I only ask you to prove n cross n is countable. How do you prove it? You just go through this. You have to clearly mention how do you get this integer n, and how do you get the the natural number n and the natural number l. Okay? Do I make myself clear? So if I give you the problem, say prove that n cross n is countable, you really need to construct this G of J equal to some lattice point so that n is uniquely determined and L is also uniquely determined based on J. All right? So that's a first first part, the Cartesian product. And second, let's see the countable union. The countable union. So for AJ is at the most countable. There is an onto function phi j from n to aj. J is from 1, 2, 3, and so on. Then we define f from n cross n to the union of aj. J belongs to the natural numbers by f n m is phi n of m. The x coordinate gave us the index of the function, and second, a y coordinate gave us the index for the evaluation of a phi n. Okay. Then this f is onto, because each phi n is onto function, so f is onto, and we just know that n cross n is countable. Or here we use the function g defined in part 1. You directly use the function g defined on part 1 from g from n to n cross n, and then you compose it with f to the union of aj, then you get the countable onto function from n to the union, countable union. So ajj belong to the natural numbers is at most countable. All right, so this is at most countable function. This is at most countable set. All right. Okay. So after those preparations, we can easily see something. First, the set Z. Z is the natural numbers union negative natural numbers union 0. The finite unit is also a countable unit, so then this is a countable. And rational numbers means you get union of p over n. P belongs to the natural numbers, n belongs to p belongs to the integers, n belongs to the natural numbers. You get 1 over 1, 2 over 1, 3 over 1, 4 over 1, whatever. And 2, n is 2, you get 1 over 2, 2 over 2, 3 over 2, 4 over 2. I don't care if it is repeated or not, because when you put the union together, if the elements are repeated, you just ignore the repeated copies, right? So here you have positive and negative. It includes all the integers. Every possible rational numbers will be included in this countable union. So this is a countable union of at most countable set is countable. It's countable. Okay? R. R is uncountable, right? If the set of irrational number, what is a set of irrational number? Real but not rational is irrational. If this set is also countable, then we get the union R without Q, union Q, countable. But this is equal to R. Right? You have two parts. One part is countable. The other part is also countable. You put them together, they are countable. The union is countable. But we already know that the union is uncountable. Hence, R without Q, the set of irrational numbers, is uncountable. Irrational numbers. The set of irrational numbers are uncountable. There are so many irrational numbers. Okay, so even though there are so many irrational numbers, but whenever you get a concrete number, you want to determine if it is rational or irrational. It's not that easy. Okay, so to determine an individual point, a number to be irrational is not an easy job. So you will see later in the future how do you determine the natural number base, natural exponential function base e and pi, they are irrational. It's not that easy. It depends on some other analysis. Of course, square root of 2, square root of 5, they are irrational. We already proved, right? We already showed that square root of 2, square root of 5, they are irrational. But other numbers are not simple. Okay? Okay, so here we use the countable union. And you have countable union, we also have uncountable union. Okay, let's see how we write them. So a collection of sets E, a set of sets, okay, a collection of set E is said to be indexed by a set A if and only if there is a function capital F from index set A onto a set of sets E, collection. Okay, so technically speaking, the set of set is not a good notation, but collection is the same thing as a set. Okay? Okay, so a function from A onto E. Onto E means every element in E, every set in E, it can be uniquely determined by an element in A. Okay, so this A is called the index set of E. Usually if we write E as a set of sub E, because A is the index set, we may write this by E sub alpha. Alpha belongs to A. So for example, when we have those index set as natural numbers, we may say the collection of a set E sub n, n belongs to the natural numbers. Then in this case, it's a countable index set. N is a countable. And when we use A can be countable, A can be uncountable. Okay, so usually if it is indexed by A, we may, in our mind, we may emphasize it is an uncountable index set. Okay, countable or uncountable index set does not change a lot, but it will change the countability for the union, while the definition of union and intersection does not change. So let E alpha belong to A is called the E, be a collection of sets. Okay, we have a collection of sets. Then the union of E is a set union E alpha belong to A is by definition X belongs to E alpha for some alpha belong to A. This is intersection. Second is intersection. Intersection of E is a set. Intersection of E alpha belong to A is X belongs to E alpha for all alpha in A. Here is a sum. All right. If you don't have index set, what is a union and intersection? Union, you may write it this way. Right? You just put E in a collection of the sets, and that's enough. And the intersection will be the same. E belong to X belong to E for all E in this. This one is a regular standard definition for the union and the intersection. There's no trivial. There's no special thing. Okay. Well, from the standard set, theoretical part, we have this the Morgan's law. The Morgan's law. The De Morgan's law says let X be the universal set, be a set E alpha belong to A, be a collection of subsets of X. Then for each subset E in X, EC, the complement, represents the set X without E. So it is complement. Then we have, if you get a union of E alpha, you get complement, it is equal to the intersection of E alpha, complement. And if you have intersection of E alpha complement, it is equal to the union E alpha complement. They are like conjugate operation. when you consider the complement. All right. Okay, so it's a very standard result from the set theory. We just prove one, and you can try the other one. Both proofs are required. You should be able to reproduce the other part. Okay, so let's, which one? Okay, let's prove the second part. The first part is proved in the book. So we want to show the second one. Show the second one, the equality of two sets. So we're going to show one by one. So let X belong to the intersection E alpha complement. Okay, intersection E alpha complement. Then this means X does not belong to the intersection E alpha. Okay, in the complement it means it's not in the intersection. It's not in the intersection. What is the intersection? Intersection means it has to belong to every E alpha. Not in it, then there is an alpha in A such that X does not belong to one of them. Okay, it does not belong to E alpha is equivalent to X belong to E alpha complement. It belongs to E alpha complement by the definition. It belongs to E alpha, belong to the union of an E alpha complement. All right, it belongs to the union of E alpha complement. So we prove from left side to the right side. So we get the intersection of an E alpha complement is a subset of a union of an E alpha complement. Okay, so this is one direction, from left to right. From right to left, let X be in the union of E alpha complement. Then this means there is an alpha in A such that X belongs to the E alpha of C. It's in the E alpha of C. It's not in the E alpha. If it is not in E alpha, then it means X does not belong to the intersection of E alpha. If it does not belong to 1, it will definitely not belong to the intersection. Intersection means it has to belong to every element, right? Okay, then this means X belongs to the intersection E alpha, alpha belongs to A, the complement. So we get from right to left. This implies the union of E alpha C is a subset of intersection E alpha, alpha in A, and then complement. So you get first this part and this part, you combine them together, the second proof, the second statement is proved. Okay, so this is De Morgan's law. Okay, so the rest of the part is about the inverse image. We will discuss in the next video. Okay, so try to understand the proofs, and especially memorize the proof from natural numbers to the product of natural numbers. See how we get the concrete construction. Okay, so we finish this video and we continue next video. Thank you.